Yeah, so thank you for inviting me here. Really great to finally give talks in person. And so today I'm excited to talk about some of our latest work on understanding complex human activities in long videos. So before I go into technical papers and approaches, I wanted to take a step back and briefly talk about the high-level goals of my research. So essentially, the ultimate goal of my work is to build computer vision models for understanding human behavior. And what does it mean exactly? Well, imagine having a personalized AI assistant in your AR glasses, let's say, and that this AI assistant can help you with a variety of daily activities like cooking, cleaning, assembling furniture, and so on. For example, maybe you're misplacing the keys in your apartment, and this AI assistant is helping you to locate them. And there's a bunch of cool applications in this area. And so I argue that in order to develop such a personalized AI assistant, at the moment, we need to focus on two important research areas. So first of which is multimodal perception, and the second of which is long-range video understanding. So for multimodal perception, of course, we know that as humans, we perceive the world around us, not just using vision, but using a bunch of different modalities like audio, speech, tactile senses, and so on. So we also want to inject the same kind of capabilities into our computational models too. And for long-range video understanding, this is also very important because if we want to build this highly effective personalized AI assistant, of course, we want this AI assistant to be able to watch these videos, understand what's happening in them, what the person is doing, and then maybe infer how in that situation the AI assistant can assist that person. So that's kind of the motivation. And this is in contrast to most prior video recognition approaches, which predominantly focus on very short range videos. So typically lasting for just maybe from 5 to 10 seconds and analyzing actions, manually trimmed actions containing very simple, basically simple atomic activities. Okay, and so with this motivation in mind, I will now present the first paper in the series called Learning to Recognize Procedural Activities with Distant Supervision, which is in collaboration with my colleagues from Meta. And so to start to motivate this paper, let's imagine the following example. So let's assume it's Friday night. Maybe you're watching some Gordon Ramsay's cooking videos, and suddenly you get inspired to make one of his favorite dishes, such as beef Wellington. So what do you do in this case? So you probably look up some online recipe or maybe some instructional video just to make sure you can complete this task. And so now with this recipe fresh on your mind, you're able to complete the first step, which in this case is searing the filet mignon. And similarly, then maybe you can also complete the second step, which is frying the mushrooms. But now maybe you already spent 15, 20 minutes, preparing these first two steps. And now the other steps start fading away from your memory. And so for me, certainly happens all the time, and this is super annoying. But luckily in this case, you have this personalized AI come to your rescue. And so in this case, this AI assistant can analyze what you've already done so far. It can understand that in this case, you're preparing this beef Wellington recipe, and it can suggest the next step that you need to perform in this case. So that's kind of the high level motivation of this paper, but more concretely, we're focusing here on the problem of classifying very fine-grained multi-step activities in very long instructional videos. So instead of just focusing on videos of 5 to 10 seconds, these procedural videos are typically lasting for several minutes in duration, so a very different setting. And so one of the biggest probably drawbacks in this research area is that most of the data sets that we have related to procedural activity recognition, that they're very small. And so this is understandable because, as you can imagine, manually annotating these long untrimmed videos is extremely costly and time consuming. So in this case, we would have to annotate temporal boundaries and also actions associated with those temporal boundaries, which is, again, it's very costly, as you can see in this case. So how do we deal with this issue? So some prior work has showed that it's possible to learn these very effective video representations without any manual annotations, just by simply forcing the video models to match the corresponding automatically transcribed speech transcription, so as is shown here. But what are some of the problems with the ASR-based methods? So the problem with this automatically transcribed speech is that it can be very noisy. And so the noise comes from different kinds of errors. So for one, ASR transcription can be imperfect. Two, there's a bunch of misalignment issues, usually between video and speech. And three, even if everything else is good, people's descriptions might not be very accurate. Maybe they're rambling about completely irrelevant things. And so just in general, our point is that ASR is probably not the best supervisory signal for the video representation learning. So what do we do instead? And so to illustrate this point, so here's a segment illustrating some of the issues with ASR. So here I'm highlighting one of such descriptions. And so in this case, you can see that the ASR, instead of describing the action that the person needs to perform, it's focusing on the type of screws that the person needs to operate on. And so while this is not a completely useless description, but we want our representation to focus on actions instead of these secondary descriptions. So we believe that ASR is not the best form of supervision in this case. And so to address this issue, what we propose to do is we propose to use this external textual WikiHow knowledge base. So this is a crowdsourced multimedia repository containing over 230,000 how-to articles. And so these articles contain very detailed descriptions of how to perform lots of different activities. So cooking, making various forms of crafts and arts, home improvements, and so on. And so here I'm visualizing one of such articles of how to cook salmon fillet, and you can see that it has these very detailed textual descriptions associated with this activity. And so our motivation is that maybe these descriptions will provide a better supervisory signal than the raw ASR. And so here we propose this distance supervision framework. So the high level idea is that we want to use a pre-trained language model to match these noisy ASR transcriptions to the detailed descriptions in this external textual WikiHow knowledge base. And so again, the motivation here is that we believe that in contrast to noisy and unstructured ASR, these more detailed WikiHow descriptions will provide a more salient supervisory signal for video representation learning. So the way we do it is very straightforward. So for every given ASR segment associated with a video, we simply try to match it to every single step in the WikiHow knowledge base. And then we just assign the best matching step to that particular video segment. And so this can then be used as a supervisory signal for our model. And of course, we can do this for every single video segment here. So pretty straightforward, just pretty much relying on a textual similarity, which is computed using a pre-trained textual model. And so I guess before I go into technical details, one thing to emphasize here is that we're not using any manual annotation. So again, just like with the previous approaches of using ASR supervision, here, everything is coming from this publicly available WikiHow knowledge base, so no manual annotations are done in this case. And so more formally, how this matching is done, so we're simply trying to compute this conditional distribution over the steps executed in the video. So this distribution of P of Y over X, where here Y is this language-based description of step S for task T coming from the external knowledge base. XL, here's a video segment L from this long instructional video X. And so then we basically compute the similarity. So here AL is a ASR associated with the same video segment L, and Y again is the language-based description of step S for task T. And so here S is this the textual similarity that we use, which in this case is just simply a normalized dot product. So nothing really fancy here. And then to obtain a proper probabilistic distribution, we can normalize over all similarities, basically with respect to all step descriptions for all tasks. And this allows us to obtain this target distribution P. And so once we have that, We can then optimize our video model. So in this case, basically our video model in this case is denoted as FC. So we feed our video model, well, we process the video, we obtain a target distribution FC, and we basically use KL divergence loss to try to match it to the target distribution P. So that's kind of the simple idea that we use, but it turns out that it's quite effective. And so experimentally, the setup is as follows. So we do the pre-training on the large scale how to 100 million data set. So many of you are probably familiar with it. It's a large scale instructional data set containing more than 100 million videos, illustrating people performing a bunch of different activities, like cooking, making bunch of improvements to home, repairing cars, doing all sorts of arts and crafts. So many different activities, more than 23,000 types of activities. And then once the pre-training is done, we do the evaluation on smaller, manually labeled procedural activity recognition data sets, so namely Coin, Breakfast, and EPIC Kitchens. So Coin and Breakfast, they're these long procedural activity recognition data sets. Coin contains about 11,000 videos spanning 180 procedural activities. Breakfast is slightly smaller. It's about 2,000 videos spanning 10 complex recipes. And then EPIC Kitchens, this is a large-scale egocentric video data set containing 100 hours of videos of people performing actions in the kitchens. And so now on the first experiment that we conduct is just basically trying to compare different forms of supervision. And we do this on a Coin procedural activity classification task. So here, our method is denoted by this purple bar. So this is our distance supervision framework. I'm not going to go through every single baseline here, but we'll try to highlight a few interesting trends. So the first interesting trend is that compared to this MIL-NCE baseline, which is essentially the prior work that I briefly described a few minutes back. So we just try to force the video representation to match the corresponding ASR. So we can see that compared to this prior work, our distance supervision framework is much more effective. So we get more than 3% boost compared to this prior work. And then even compared to the fully supervised kinetics pre-trained baseline, which is depicted by this red bar, we can see that our model outperforms the fully supervised baseline by more than 2%, indicating the effectiveness of its supervision coming from the external textual knowledge base. And then we also compare our method on 4 downstream recognition tasks, so namely step classification on Coin, task classification on Breakfast, step forecasting on Coin, and egocentric video classification on EPIC Kitchens. And so here we show that, especially on the first 3 tasks, we easily beat state of the art. Yeah, and so again, kind of showing that our model generalizes quite well to a lot of these procedural activity recognition data sets. And even on this challenging EPIC Kitchens data set, we see that we don't get the best performance, but we get pretty competitive numbers. And again, considering the fact that we never pre-train on purely egocentric video data, I think this shows that the generalization of our framework is pretty solid. Yeah, so the main take-home message here is that the distance supervision framework that we provide, so essentially using this external textual WikiHow knowledge base, allows us to learn a very strong visual representation that generalizes on a wide array of procedural activity recognition tasks. So I'll leave questions to the end, and then I'll continue with the second paper. And so in this case, this is called Eclipse. For efficient long-range video retrieval using sight and sound. So this is a collaboration with my UNC colleagues. So in this case, the problem that we're focusing on is a long-range text-to-video retrieval. So given a textual query describing a several-minute-long video, our goal is to retrieve the correct video. And again, the motivation here connects to the same personalized AI assistant idea. Again, if we're sticking with this Beef Wellington example, if you forget one of the steps, it would be great to be able to just issue a verbal query and try to retrieve maybe a relevant several minute long video segment that would inform you what to do next. So that's kind of the motivation. And again, the prior work is not really applicable in this setting because most of it focuses on very short range videos. So typically lasting from 5 to 15 seconds in length. So you can't really apply these methods very successfully on these long videos lasting for at least several minutes. And so another prior work that I wanted to mention here, because we're going to be relying on it a lot, is CLIP. So as most of you are probably familiar with, CLIP is one of the most widely adopted vision language methods nowadays. And because of its strong pre-training and very good generalization ability, one of our goals in this work is to reuse CLIP. And so the key challenge is that, of course, CLIP is only trained on image data. And in this case, we need to extend it not only just to videos, but to actually very long videos. So that's a challenge that we're going to be trying to address in this work as well. So the motivation for this paper is quite simple. So our key observation is that while videos are, they're very rich in the information they store, but can also be very expensive to process, especially if we consider very long videos consisting of maybe hundreds of frames. And they're also extremely redundant. So if we look at the neighboring frames, typically we don't see a lot of visual change in there. So costly and redundant. And audio, in contrast, has very different and I would say complementary characteristics to video. So in contrast, audio is quite compact. And it also, as demonstrated by prior work, audio can be used to recognize objects, actions, complex activities, scenes, many other things. So even though it's compact, it can accurately capture lots of visual content as well. And so it's also much cheaper to process than the video. And so that's kind of our motivation. We want to leverage these complementary characteristics between video and audio. And so to demonstrate how useful the audio can be, let me play the following video. Let's hope the audio plays okay. So you can basically see that in this video, Gordon Ramsay is again preparing some recipe. He's chopping. We can not only see that he's chopping, but we can hear. Then he's whisking, and again, the sound is very prominent. So just based on the audio, even without seeing any of the video, we will probably be able to recognize what's happening in this video. So that kind of motivates us to incorporate audio in this case. And so specifically, we propose this Eclipse framework, which stands for Efficient Clip with Sound Encoding. And the idea is pretty simple. So instead of operating on these densely sampled long videos, which can be very costly and wasteful because the videos are redundant, in this case, we propose to operate on sparsely sampled videos that are also accompanied by densely sampled audio. So that's the main idea. And so to do that, we propose this architecture that essentially extends CLIP from image setting to the long-range text-to-video retrieval just by simply adding the efficient audiovisual attention block into our architecture. And so let me now quickly walk through how we do this. So as our inputs, in this case, we're taking the video patches and audio patches. So just basically fixed embeddings that can be fed into a standard transformer model. And so for the video, we just patchify the video and obtain embeddings, similar as is done in VIT. For audio, we use a pre-trained audio encoder. So it processes raw audio spectrograms and outputs some features that we can then feed into this into our backbone. And we also use this same scheme for text. So we have a pre-trained text encoder, in this case, BERT. And so it processes our textual query and outputs features that we'll be able to then use to train our model. And so once we have these embeddings, now we can feed the video and audio embeddings into our audio-visual Eclipse backbone. And so the idea behind this backbone is that it allows us to inject relevant video information into audio and conversely relevant audio information into video. So here's how it happens. So it consists of three attention schemes. So the spatial attention, cross-modal attention called audio to video, and then another module, cross-modal attention called video to audio. And so these are just basically, well, so I'll go through this, but so now the main difference with respect to standard clip is that now instead of just using spatial attention, we have these three different attention operations in each layer. And then these audio-visual attention layers are essentially just stacked on top of each other, typically 12 times, as is done in the standard transformer architecture. And so now let me go through each of these attention layers in more detail. So for the spatial attention, there's nothing really special. Just to preserve the pre-trained clip architecture, we are reusing their weights. And at a high level, this just allows us to compute discriminative frame level representation, just as is done in clip. So then for the first cross attention layer here, audio to video, this allows us to inject relevant audio cues. So these long range temporal audio cues into the video representation. And at a high level, the way it's done is just, so the new video representation is essentially computed as a weighted summation of all the audio tokens. So I'm not gonna go into too much detail, but it's a pretty straightforward PyTorch operation. And then conversely, we also have this video to audio attention. So we also wanna basically make the audio a little bit more expressive by injecting video cues into audio. And so here, again, at a high level, we're just simply, the new audio representation is computed as a weighted summation of the video tokens. And so this can also, again, all the details are in the paper, but this can be done pretty efficiently. So that's kind of, and as already mentioned, so this block basically, so this is a basic block that we use to build our transformer model, and we can then just stack it as many times as we need. So again, typically 12 times, and that's going to be our Eclipse transformer model. And so once we do that, we then train our model using a contrastive text to video loss. So I'm not going to cover this because this is very standard. Pretty much all the text to video retrieval papers use this. Yeah, so nothing sophisticated here. So let me go now through the experiments. So we validated our approach on the ActivityNet captions dataset, which is very well suited for this setup because so it has about 20,000 videos where on average, each of these videos lasts 3 minutes in duration. So much longer than the standard benchmarks, typically lasting from 10 to 15 seconds. And so here we evaluate the accuracy using standard evaluation metrics. So mainly the text to video retrieval at recall at 1. And so this essentially just measures the fraction of times that we retrieve the correct video. And then we also include the computational metrics to measure for efficiency. And so these include GFLOPS, GPU memory consumption, and runtime in terms of samples per second. And then at the plot below, we also, we just plot the accuracy as a function of number of input frames. So here we compare our Eclipse model with this very strong clip for clip baseline. Clip for clip is a pretty straightforward extension to video. So at the time when we were working on it, it was state-of-the-art video retrieval model. So it was a good baseline to use for comparison. And so here, what you can observe from the table is that despite using 3 times fewer frames than clip for clip, so clip for clip uses 96 frames in this case, whereas our method uses 32 frames, but also plus audio. So we're able to obtain better accuracy while also being significantly more efficient. So you can see in this case, our framework requires 2.3 times less GPU memory, and it's about 3 times faster than clip for clip. Again, mainly attributed to the fact that we use significantly fewer frames. And so also in the plot below, we showed that basically for every setting here, our method outperforms the clip for clip. And again, even if using 3 times fewer frames, we're still able to get better numbers. And then we also show that our method generalizes to other long-range video retrieval data sets. In this case, we tested on other 4 data sets, namely QV highlights, the demo, UCook2, and charades. And again, in this case, we showed that in addition to having better accuracy than these other methods, our method is also more efficient as is measured in the theoretical measure of G-flops. And also, so we observed, interestingly, even though we never really trained our model to do any sort of sound localization, just as a byproduct of doing this text-to-video retrieval, we observed that the model learns quite well to do sound localization as well. So here I'm visualizing some of our results. Okay, so the take-home message here is that we propose this Eclipse framework. And so we showed that in this case, maybe quite surprisingly, but audio can be effectively used to replace these redundant and very costly to process video parts. And that this becomes very useful when we start considering long-range video inputs, and so specifically for this problem of long-range text-to-video retrieval. And so the last paper that I wanted to present here is long movie clip classification with state space video models, which is work done with my PhD student, Mohamed. So the motivation here is very simple. So we all know that applying transformers to long videos is costly. And so just to illustrate this point, let's assume in this case, again, we're processing these long videos, let's say lasting for 60 seconds. So sampled maybe at 1 FPS. So 60 frames, and let's say each frame consisting of 196 tokens. So in total, this would be about 12,000 tokens. And so if we apply standard transformer on these kinds of inputs, pretty much every self-attention operation would require 1.4 million pairwise comparisons, which is, I mean, it's a huge amount of computation, completely unscalable. And so this is only 60 seconds. So imagine if we had to do this for maybe half an hour. I mean, this would be completely unscalable. And so there are prior work that try to develop these more efficient attention schemes for video, but unfortunately, while they manage to improve efficiency, but this often leads to a substantial drop in accuracy. Again, we don't really want to make compromises between efficiency and accuracy. So here, to address this issue, basically, we look at this fundamental structured state space model. And so this is, for those of you who are unfamiliar, so this is kind of this old school basic model that is commonly used in fields like computational neuroscience or control theory. And there's nothing really too complex about it. It's essentially a recurrent model that's parametrized by these 4 matrices, A, B, C, and D. And so essentially it just, it basically computes, so given input sequences U, it uses these 4 matrices to compute the output sequences Y through mapping the sequence inputs to the latent variable X. And so again, it's essentially, you can view it as a simpler LSTM model. It's just a recurrent model. And the reason why these models are not very popular, because while in theory they can be used to model long-range dependencies and sequential inputs, but in practice, when you try them, they actually struggle even with very basic tasks. So I think that's one of the main reasons why probably you haven't heard about these models. But the reason why we got interested is because recently there's been some theory on these models, so specifically this paper that I'm referencing here, that showed that if you initialize this matrix in a very specific way, then you start getting some theoretical guarantees that this model is gonna start modeling long-range dependencies quite effectively, but also empirically, it starts working quite well. And so to show the empirical effectiveness, the authors from the paper, they tested on the long-range arena benchmark. So this is typically benchmark used for NLP models. And so here they show that these structured state space models, which for short they stand for S4, they can outperform lots of these, so standard self-attention based models, but also all of these efficient attention schemes, as you can see in this table. And so even more interestingly, you can see that there's some of these tasks are actually very challenging, like PathX. And you can see that none of the methods are able to solve it, but these S4, so these state space based models are the first method that are able to solve it. So these results kind of got us interested in this model, and so specifically in its applications for video. And also the nice thing about this model is when you look at its theoretical runtime, we see that in contrast to attention, which has a quadratic dependency on the sequence length L, these state space video models, they're much more efficient. So they only have linear dependency to the sequence length. So again, sort of these quantitative results, as well as the theoretical runtime guarantees, got us interested in how these models would work in the video domain. And so here, basically, we proposed this ViS4mer model. So I'm not going to spend too much time on this because I already spent quite a bit of time on this presentation, but I'm going to try to cover high-level intuition. And if you're interested, check out our paper for more details. So the main motivation here is to basically combine the strengths of short-range modeling of transformers and then long-range modeling of these structured state space models. And so in particular, what we do here, given these long video inputs, let's say lasting for 60 seconds or even more, I mean, these S4 models can handle very long video sequences, so we're not restricted to 60 seconds. So it's just an example. But so the first step that we do is we use a short-range transformer encoder to extract short-term features. And so these transformer encoders, this can be a timesformer or a video swin or any other short-range model. And the intuition here is that we already have a lot of these models that are able to model short video clips very well. So we want to reuse it. But of course, a lot of these models are completely not suitable for long-range sequence modeling. So in this case, once the short-range transformer encoder extracts these features, we can then attach this long-range temporal S4 decoder to try to model very long-range dependencies over the whole video, so over this entire 60-second video. So that's kind of the high-level idea. And this S4 decoder, so it's a little bit more complicated that I'm showing here. And again, if you're interested, check out the paper. But at a high level, it basically tries to, it implements this operation that I listed previously. So using those like 4 matrices, A, B, C, and D. But so the nice thing also that the authors in the paper that I referenced showed that it's possible, you can basically eliminate this recurrent computation, which it's very inconvenient when training large models, and you can actually convolutionize everything. So in this case, instead of using directly these 4 matrices, you can just apply this operation here that I'm showing at the second row. And this K, it is essentially a convolutional kernel that now you can use to obtain the same result. And so now this can be implemented very efficiently. You can train it, you can enjoy these like parallelization benefits of convolutional models. And so there's no efficiency issues, and it still implements the same operation as a theoretical model. So that's kind of the main idea. And so immediately once we implement this, we can observe that there is huge efficiency gains. So for example, here we compare with the pure transformer baseline. So for example, here, if instead of this temporal S4 decoder, if we just attach a standard transformer, so that model would require about 41 gigabytes of GPU memory, which is, it's quite a lot. But our model, if we replace these self-attention based layers at the end with the state space layers, our model only requires about 5 gigabytes of GPU memory. So about 8 times savings. And then we also tested on the same procedural activity recognition data sets like coin and breakfast. And we showed that in this case, so compared to the baselines that use the same similar amount of pre-training data, so namely kinetics, we outperform those baselines by a pretty big margin. And then compared to the distance supervision framework that I introduced earlier, we're able to obtain competitive results. But again, as you can see, we're using, in this case, significantly less amount of pre-training data. Performance is also pretty reasonable in these cases. And we also compared to more efficient self-attention schemes. And so in this case, we do so on this long video understanding benchmark, which basically captures 9 movie understanding tasks. And in this case, we show that not only is our state space based model more efficient in this case than these standard self-attention, but also more these efficient self-attention schemes like PerFormer or OrthoFormer, but it also achieves higher accuracy on 8 out of 9 movie understanding tasks. And so the key message here is that this model allows us to combine the strengths of self-attention and structured state space layers to build a memory efficient long-range video classification model. So that's pretty much all I had, and I'd be happy to answer any questions now. I can see Zoom, so yeah.
The EPIC model, I'm not sure whether I misheard something or do you use somehow the weights or?
Okay, so I guess this is the part that I forgot to mention. So so basically, one important thing is, again, as I mentioned, that we want to preserve the clip structure. So the spatial attention layers here, these are just copied from clip. And basically, so how do we do this? Because now we have these injected cross attention layers. I mean, the original clip doesn't have them. So the idea is quite simple. So we have residual connections attached to every one of these cross attention layers. And these residual connections are basically initialized to 0. So at the very first iteration, once we start training the model, it's actually exactly the clip model. So these cross attention models are not contributing at all. It's just a clip. They're there, but they're not doing anything. And so once we start training, the model starts gradually learning to incorporate relevant audio information into video and vice versa. And so this kind of gives us the best of both worlds, that we're able to reuse a strong pre-trained clip model, but we're also able to gradually inject relevant audio information into video.